All right, more magnetism. Okay, a wire 1.6 meters long experiences a magnetic force of 0.85 newtons due to a perpendicular and uniform magnetic field. That's fancy talk for basically the magnetic field is pointed at 90 degrees to whatever my current is, which is good. That gives us the sine of the angle between them as 90 degrees, which is just 1, so we're just going to ignore the angle. And then uniform tells us that the magnetic field doesn't actually change, which is really good because otherwise we'd have to use some calculus. All right. If the wire carries a current of 10 amps, what is the magnitude of the magnetic field? So, what I'm going to draw here, it doesn't give us much in the lines of directions, but that's okay. I'm going to draw a piece of wire, and I'm going to say that we have a current that is going to the right, like this. And they say that we have a perpendicular magnetic field. So I'm going to say that the magnetic field is actually straight down. Doesn't matter, it could be straight up. Or into the board or out of the board. The one thing that it cannot be is slightly to the right or slightly to the left. It must be either straight up and down or in and out or some combination of those, but it cannot be left or right because then it would not be perpendicular to the wire. In short, we've got 90 degrees between them. We are looking at a section of wire that they say is 1.6 meters long. It experiences a magnetic force, so a Lorentz force, Fb, of 0.85 newtons, and it has a current of 10 amps. The question is, what is the magnitude, what's the strength of the magnetic field? Well, here's where we use the other equation that we have for the Lorentz force. It is the current times the length of the wire, technically crossed with the magnetic field, but we're going to do ILB sine theta between. And like I said, very rarely, if ever, will I have you deal with anything where the angle is something fancy. So this, because it is perpendicular, our magnetic field is down and our current is to the right, is 90 degrees between them, so this whole thing is just 1. Here's where we can start filling some things in. We're solving for B. So the force, they told us, was 0.85 newtons. Our current was 10 amps. Our length was 1.6 meters. And we do not know the magnetic field. That's actually what we're looking for. So here we go. I'm going to take 0.85 divided by 10 divided by 1.6. And if I've done this correctly, my magnetic field strength should be 0.05313. Put SI in newtons, amps, and meter. You get SI out. This will be in Tesla. Let's see what the expected answer is. 0.5313 Tesla. So this is the correct answer. This is what we're looking for. And this is how you would go about doing it. We apply the different Lorentz force equation.